Swayam Prabha. Digital India. Educated India.
In the last class, we had seen what is the brief outline on the course on engineering fracture mechanics. Then the concepts from strength of materials were reviewed. The idea that was emphasized was whatever the concept that you had learned are very useful, but the knowledge you gained is limited. And when you want to characterize the material, one of the simplest tests that was done was tension test. The focus on the tension test was you have an elastic region followed by a large plastic zone, then only the material fails. But once people had moving parts in the design, like locomotives started failing, people felt a simple tension test is not sufficient to characterize the material completely. Something more needs to be done. So, this prompted the use of designing a new test, what is known as a fatigue test. And we had also looked at, the focus was to find out, apply a repeated loading on the specimen, and the test was confined to measuring only the number of cycles when the test specimen fails eventually. So, you do not record any other information in between. So, it is a improvement from a simple tension test. In service condition you have repeated loading. So, you have been able to simulate a repeated loading and also perform a test until the specimen breaks. So, you collect voluminous data and this data is presented in a nice form for you to process. And you have a log plot of the stress applied and the number of cycles to failure. In fact, arriving at what should be the way x axis to be plotted and y axis to be plotted is not simple. And what you see here is you have a scatter of data. This is an indication of an experiment well performed. So, in an experiment normally you will have scatter of data and you take your time to make a sketch of this graph. Whatever the data that you have got, you need to make some sense out of it. If you look at the genesis of concept of stress as well as strain, it started from performing load elongation curves. Then instead of plotting as load elongation curve, if you plot it as stress versus strain, you will have just one graph for a given material. So, if you look at any development in engineering, collecting data is one aspect of it, reporting data and trying to find out a meaning from the data is equally challenging. So, in the case of a fatigue test, they decided to plot a log graph between the life is in number of cycles and you have the y axis is whatever the amplitude of the alternating stress divided by the ultimate tensile strength. And what you find here is you are in a position to draw a line like this that gives the least expected life n for a given alternating stress S. And you also have, from a design point of view, a convenient parameter called the endurance limit. So, what you find is if you load the specimen only to the endurance limit, it gives an impression that you will have infinite life without any problem. It is very convenient parameter from design point of view. See, the modern research tells there is nothing like endurance limit for any of the material. Every material fails after sufficient number of cycles. And you will also have to appreciate one more aspect, when you have got this endurance limit for which you have to perform a fatigue test, there are also attempts to find out an empirical relation involving the result of a tension test. And what you find here is the endurance limit is given for this rod steel as 0.5 times the ultimate tensile strength. So, what you find here is the development of SN curve for designing structures with infinite life came into vogue then. So, that is an improvement from tension test. You have graduated to simulate what happens in actual service condition, if not completely, at least very close to simulating alternating loads on the structure, because when you do a fatigue test you go for a sinusoidal loading. If you really go to actual service condition, you will have variable amplitude loading, which could be using Fourier series, you will be able to convert that as series of sinusoidal loading. And there are ways, fatigue itself is a vast subject, there are ways how to count the number of cycles, in what way you have to go about, so on and so forth. But the important aspect here is you have been able to improve your design methodology by bringing in the aspect of alternating load. Definitely this approach to some extent has recognized the failure due to crack growth. We have already seen how the test was performed. The test was performed only to record the number of cycles. So, there was no provision to monitor the growth of a crack or predict the remaining life. So, this we look at from the point of view of fracture mechanics. Now, we know crack is very important, it grows, growth has to be understood properly. Then you say that you will have to find out even the data pertaining to crack growth, but considering the tension test, definitely fatigue was an improvement. So, obviously for damage tolerance approach to be effective, one needs to devise more comprehensive tests that give information on crack growth behavior. So, this is very important, without which you will not be able to do a damage tolerance approach. So, anticipate that we will have to have a new test if we have to practice fracture mechanics. And before we go into that, let us look at what we have been doing in conventional design. The conventional design approaches are done with the premise that the material is an elastic continuum without any material defects or flaws. See, this is how you can proceed, because even if you read mechanics, you start from rigid body mechanics, then you graduate to deformable solids. When you go to deformable solids, what do? You do not directly take up nonlinear behavior, you idealize the deformation as small and it is also linear, it makes your life lot more simple. On the similar vein, when you have started modeling the material behavior, it was convenient, purely out of convenience you consider that it is an elastic continuum. And what are the design approaches you had? You have one approach design based on strength, there is another approach design based on stiffness. So, in design based on strength, what do? You determine the cross section and choose a material such that the stress at any point in the structure does not touch the yield stress of the material, because we have already seen in the case of conventional design approach, yielding was considered as a failure. And I have also mentioned most of the mechanical and aerospace components sell well below the elastic limit. So, it is a good starting point. So, you limit your stresses such that they are well below the yield stress. And one of the other important aspect of conventional design approach is you do not operate with the yield strength to start with, you bring in a factor called factor of safety because there may be mistakes in calculating the service loads, there may be overloads, there may be material defects. So, to take care of all these aspects, you bring in a concept of factor of safety, and you have seen in several designs it ranges from 2 to 10. So, this is always used to decide the maximum stress allowed to take care of improper modeling of service loads, material properties, as well as protection methods. And if you really look back, if you have this cable ropeway cars, where you have very difficult service condition and safety is very important, and it is also exposed to gusts of wind, and you have factor of safety of the order of 10. On the other hand, if you come to our ambassador cars, this was operating with a factor of safety of 4. On the other hand, if you look at Maruti, it is of very thin sheet metal work, and there is also a demand on fuel consumption reduction. So, they want to bring down the dead weight. So, they bring down the factor of safety. When you bring down the factor of safety, your analysis has to be more and more precise. So, you have to have a trade off between cost for analysis and the gain you get out of it. Obviously, the aerospace structures, if you do the analysis, the gain is more. For very conventional day to day activities, you want to have a foolproof design methodology that would give you reasonable values on the final cross section. So, that there is a trade off between detailed analysis and a simplified procedure. So, one of the design approaches is you do it design based on strength, and you essentially determine the cross section. If you find the cross section you cannot modify because of certain restriction, you can choose a better material to withstand higher stresses. The other design approach, what you have is designs based on stiffness. For many of this mechanical and aerospace components, the satisfactory performance of the component depends on deflection or deformation, whatever that comes across. So, you limit the values on the deflection, so that you find out what is the geometry or what is the cross section that you have to do for a given design approach. And if you really look at, when you have a shaft design, people go for mild steel, and there it is actually dictated by the deflection. If you go by the strength calculation, you will have a shaft which is of very small dimension, but from deflection point of view, it may experience a larger deflection. So, the deflection limits the size of the cross section. So, you will go for a larger size of cross section. So, in the shaft design is really dictated by the deflection, and also you find you use a low strength material for shaft. On the other hand, you have springs. Springs are made of very high strength material, and if you really look at, you have a compression spring or a tension spring, in actual practice it is really experiencing a torsional load. So, you design it for shear. So, you will have to know, you have done a course in design, you use different materials for different applications. Shafts are made of only mild steel, and when you have a spring, it is always made of high strength steel. So, the focus here is, when I have relative moving parts, the deflection or deformation plays a very important role, because you have to maintain close tolerance levels and usually design based on stiffness. And again it is emphasized, all these approaches to design are done with the premise that the material is an elastic continuum without any material defects or flaws. It is purely out of convenience, there is no other reason. If they had better mathematical model and simplified approaches, they would have also incorporated what happens when you have a flaw. Purely out of convenience, the initial design approaches were confined to considering the medium as elastic continuum, and this worked well. You could do some kind of engineering based on this, but what is the situation now? See, you have to look at the modern structural environment is much more complex in terms of operating temperatures, aggressive environments and types of loading, etc. See, now you find people go to space and come back to earth. So, they have to pass through the barrier to earth and very high temperatures are developed. It is about order of 1600 degrees centigrade. You never even dream of that kind of operating conditions earlier, and you have cryogenic engines. So, you have demands that are far different from what was initially thought of in conventional design approaches. And in addition, what you do? You also have requirement for optimization, and these optimization requirements have resulted in reduction in the weight of structures, which in turn leads to enhanced operating stress levels. So, what we want to do is we want to take out as much as possible from the material that I have put in for making a structure. So, we want to have a trade off. So, we want to have optimized structures. So, that means I should do more analysis. When I do more analysis, I must also go closer to reality, and obviously if you ignore the presence of material defects or inherent flaws, it will definitely lead to spectacular failures. In fact, that is what has happened. So, finally, if you want to have a successful design of engineering structures for long term life, requires many things. It requires understanding of the different modes of failures and degradation mechanisms. See, this was never understood in conventional design. Only in modern design you also look at there are degradation mechanisms. So, this fundamentally makes a difference in damage tolerant approach. So, you have to understand the degradation mechanisms, and what are they? Crack growth due to service loads, problems due to corrosion, and also special problem due to material becoming brittle. One of the important causes is hydrogen embrittlement, and in fuel cells one of the major drawback is the structure becomes brittle because of hydrogen entrapment, and you have nuclear power for these days, and the major problem there is damage due to radiation. So, these are all degradation mechanisms. Unless you understand the degradation mechanisms, you will not be able to provide sufficient margins against these mechanisms. So, if you know that, you could incorporate that in the design phase itself. So, the idea is the modern design will have to address the issue of degradation mechanisms. Before we really take a fracture mechanics, let us look at the spectacular failures. Why they are called spectacular failures? We are going to look at the key failures that triggered the engineering community to sit back and evaluate the existing design procedures are listed. They were very important failures. So, one famous failure was Boston molasses tank failure. This happened in 1919. In fact, I am going to give you a list of 4 such failures over a span of about 70 years. And what was important in Boston molasses tank failure? And you all know, when you travel in a train, if you cross a sugar cane factory, you have the smell of molasses. It is not pleasant to smell, okay. And certain failures are spectacular because people remember for years because of its notoriety. The problem with molasses tank failure was this left a characteristic smell in parts of Boston which remained for several decades after the disaster. So, people cannot, even if they want to forget, that such a thing happen, the smell will remind them. So, it becomes a very important, and you have to go and investigate what happened, how this happened, why it happened. So, this is what made the engineering community to think and evolve new design approaches. Another famous failure was Liberty ship failure. This is between 1942 to 1946. Exigencies of World War II put a pressure on speedy production of ships, leading to all welded design. Prior to that, people had ships made of riveted design, and it takes quite a bit of time to fabricate a ship. When they switched over to welded design, they could quickly make the ships. They also paid a heavy price for it. What happened was, the ships failed, there was absolutely no control on fracture. In fact, we would see each one of these disasters one after another in elaboration. Right now, we only have a short summary, later we will also have a look at in detail some of these failures. The another disaster which we will look at is the comet disaster. This happened in 1954. The importance of comet is, this was the first commercial jetliner put into service. Until then, they were all only propeller planes. Because it is a jetliner, several novel designs were put to litmus test, and we will see what was the problem and how this was diagnosed and solved. And very recently in 1988, you had Aloha Airlines Boeing fuselage failure. This really opened up the accelerated aging of structures due to corrosion. People ignored corrosion totally in the design. So, we will go one failure after the other. We will look at what happened in the Boston molasses failure. So, what happened was, without warning, that is a key aspect. See, you had seen a tension test, you take a mild steel specimen or a ductile specimen and pull it, you have always noticed you have a cushioning, it goes through extensive plastic deformation before it fails. So, you naturally conclude, when you make a structure out of a ductile material, it would give you some kind of a warning before it fails. What happened in the case of molasses disaster? Without warning, in January 1919, molasses surged over Boston and a frightful flood devastated a vast area of the city. You can imagine, tsunami comes and you have sea water engulfs the country. Now, we hear such disasters, and there have also been volcanoes which totally submerge the cities. All those disasters have happened, but there are no one will remind to tell you what happened. But in Boston molasses failure, very unusual, you see a flood of molasses affecting the city. You had 2.3 million gallon Boston molasses tank, which was only 3 years old at the time of failure. See, this is the pity. Now, normally when you design the structures, you want it to come for 50 to 60 years, and you do not expect a failure to happen in just 3 years. And the tank was very huge, it was 50 feet tall and 90 feet in diameter, just to give you a size. And this also gives you an idea of what is the kind of devastation that occurred, and this figure courtesy is from Boston Library. And really look at how the failure happened. The tank came apart with a thunderous cracking, and an estimated 14,000 tons of molasses caused havoc, and the molasses traveled with a speed of 40 to 56 kilometers per hour, and it was not easy to clean. It took 6 months to clean up the place. Not only this, after cleaning, if there is no smell, people would have forgotten Boston molasses disaster. The pity was, the smell was coming for decades In fact, the molasses actually continued to creep out of the ground and cracks in the sidewalks for 30 years. So, even if you want to forget, you cannot forget this. The smell remained for decades a distinctive atmosphere of Boston. And this shows another picture of how the devastation was, and this is again the courtesy goes to Boston Public Library. Let us look at what happened. First thing is, the tank was made of 15 millimeter thick steel plates, very thick, 15 millimeter thick is very large. So, one should really relax, I have made out of very thick plate, why should I worry? And what happened? Before the explosion, the tank's owner painted it brown. Even this is looked at. When you look at the failure analysis, people want to find out what kind of mistakes could have happened. What is the color of molasses? Molasses is brown. Without knowing that, the owner of the tank painted it brown. The result is, even if there is a leak, it will be very difficult to spot there is a leak in the tank, and the tank is so huge, you cannot view it unless you have a contrast in color. And in fact, in modern design, you have what is known as leak before break. In all nuclear power installations, it is mandatory the heat exchanger tubes have to go through LBB criteria. That is why I want to emphasize, in the case of Boston molasses failure, there was no scope for having a look at whether the tank was leaking. That is one indication that some reinforcement need to be done, or remove molasses, so that you bring down the pressure build up and so on and so forth. And this is very important. See, if you look at your Indian cooking gas, it is actually odorless. People have added that smell, so that if there is a leak, you would respond to it by smell and go and take corrective measures. Either you go and open the windows, do not switch on the light. Some corrective mechanism is possible if you are alerted. So, in all nuclear power installations, LBB criterion is very important. And what happened? The failure investigators found out that the possible cause was a sudden temperature change, as the temperature on the previous day was -17 degrees centigrade, and on the day of occurrence it was 4.5 degrees centigrade. So, there is a thermal shock. So, thermal shock precipitated, and what they concluded, see, in conventional design, whatever they do not understand, they put it as a factor of safety. So, it happened in 1920. So, in those days, people concluded finally that design was found to be inadequate to withstand the pressure created by expanding molasses, and the factor of safety used was considered to be low. I mean, this is too trivial a conclusion, because they were used to bring in a factor of safety. So, they concluded it failed. So, something has gone wrong. So, increase the factor of safety. So, this is not going to solve the problem, because you are not really looking at the root cause of the problem. It is only a cosmetic changes in your design approaches, and people really burned their fingers in Liberty ships. And look at over 5,000 Liberty ships and T2 tankers were mass produced during World War II. See, this is very important. It appears in the history of shipbuilding, nowhere you find a same design was used to produce such a large number of ships. If the ships were successful, no one would have worried, but you find the failures were astronomical. You have to be in shame, because the whole scientific community was clueless why such failures have happened. And you look at the failures of the 5,000 ships, 1000 suffered significant failures, and in fact, some of them broke into two. Imagine a ship breaking into two. It is made of ductile material and it broke into two all of a sudden. See, that is the most dangerous part of it. So, between 1942 and 46, thousands suffered, and because of low temperature is what they were able to identify at that time. And between 1942 to 52, they had also improved some of the methodologies, and 200 suffered serious fractures in this time frame. So, definitely you will have to look at and find out what has happened. And the observation was the failure rate of the welded ships was statistically astronomical in the North Atlantic, while literally non-existent in the warm waters of the South Pacific. So, they understood, yes, this is something to do with low temperature. Low temperature is one cause, and you also have welded ships, because previously ships were made of riveted joints, and when they moved over from riveted joints to welding, first thing they observed was there was weight reduction, very quick in fabricating the ship. I was told that within a week they could fabricate one ship. This is how they have achieved, because the war exigencies required more and more fleet to be generated at a short time. But the result was, you find there were many failures that needs to be looked at and the cause needs to be ascertained. And it is also mentioned that no one know exactly how many ships just disappeared in North Atlantic. The engineering community was clueless that low temperature can cause brittle fracture of steel. In fact, the Navy formulated a committee, a board, to go into the details and find out what really caused such failures and come out with recommendations. In fact, I have access to that report thanks to the Project Liberty Ship program, and I would read the foreword that would be more revealing. I would just read from that. See, the foreword starts like this: early in the war, welded merchant vessels experienced difficulties in the form of fractures which could not be explained. The fractures in many cases manifested themselves with explosive suddenness and exhibited a quality of brittleness which was not ordinarily associated with the behavior of a normally ductile material such as ship steel. So, they formulated a committee, and the committee was given a dictum what they should do, and that is also very important. It is very nice to see how people have looked at it. See, there are two ways. When a failure happens, you just condemn the scientists are so useless, whatever the funding we give to them goes down the drain, and condemn them and go with your life. This is one approach which we commonly come across in India, because when you have GSLV failure, people only first laugh, they do not look at there are genuine problems when you are dealing with modern technology. So, people have to be sympathetic and provide proper way of analyzing data and come out of the problem. And imagine, out of the 5,000 ships, 1,000 ships break. They had serious fractures and some of them broke into two. It is really a sort of a blot on the engineering community which designed it. But what you will have to appreciate is the fractures were very systematically analyzed. We would also see some of their graphs, and useful data was collected. In fact, it is the Naval Research Board which funded fracture mechanics research initially. So, you find fracture mechanics grew from such a study, and the board was given this kind of dictum to investigate. That also I will read. The secretary's directive to the board read in part as follows: make a complete investigation of the matter hereby submitted, and upon the conclusion of its investigation, will report the facts established thereby. And I would say it is really a scientific approach. When you face failures, investigate, find out what is the cause, so that you do not repeat it again, rather than ridiculing failures, because failure has always been a method for inventing new ideas. Without failures, nothing has happened. If you really look at the bridge design, people built a suspension bridge. After a few months of operation, it violently vibrated and the whole bridge collapsed. Then people realize resonance is very important. So, the key is when you face failures, analyze it systematically, and this was done a very nice scientific analysis. And the dictum reads like this: if the facts establish the existence of defects in the designs of or in the methods being followed in the construction of such merchant vessels, which in the opinion of the board adversely affect the seaworthiness thereof, the board will also submit its recommendations as to the measures which should be taken to correct such defects. So, it is very clear, people have realized that design is one aspect, the construction is another aspect, and how well the construction practices are enforced, because when you are doing welding, welding is a very tricky manufacturing process, and you are talking about way back. In those days, people have not fully understood the weld defects. So, the board was very scientific in its approach, open minded, and carefully collected voluminous data and beautifully characterized. And if you really look at the whole analysis, started when you had this T2 tanker Schenectady broke into two in the warm waters of in the cold waters, I should not say warm waters, in the cold waters of Swan Island, and this is the tanker. This ship broke into two, you see the fracture here, and this figure is from Project Liberty ship, and what you had was the water temperature was about 4.5 degrees centigrade. Then the problem was taken up seriously, and this shows the fracture through the deck. You can see how the entire deck has fractured. It is a very serious matter. So, what you find is these calamities focus attention on the fact that normally ductile mild steel can become brittle under certain conditions. So, if you really go to metallurgists, they have understood now there is something called ductile to brittle transition. We will have a look at it. There is nothing like a material is always ductile. Above certain temperatures, it may behave in a ductile fashion, below some temperature, it may become brittle. That kind of an understanding came about, and this is what you see in ductile to brittle transition. And it is reported that fracture toughness, which you would learn in this course, this was found to vary for ferritic steels over a small temperature range. At low temperature, steel is brittle and fails by cleavage. At high temperature, it is ductile and fails by microvoid coalescence or plastic collapse. And this is how you have, you can make a neat sketch of it. So, you plot temperatures versus fracture toughness, and the graph is like this. So, in this region the material is 100% ductile. Below this temperature, which is labeled as NDT, the expansion is nil ductility transition temperature. So, you find there is a transition zone from ductile to brittle, and what people have found is, I had already mentioned that there are degradation mechanisms, particularly in nuclear power plants. People have to understand how to safely guard the nuclear power plants. So, what they found was, when the structure is exposed to radiation, there is a drastic change happens on the nil ductility temperature, and people have understood and call it as a radiation shift. So, what you find here is the whole graph shifts to the right. So, this is called radiation shift, and you find the nil ductility transition temperature has increased. So, that means over a period of time the nuclear power installation degrades because of exposure to radiation. This aspect needs to be taken into account at the design phase itself, that is what is important. So, the Liberty ship failure has shown you very important things. There is a concept of changing from ductile to brittle, there is a temperature, transition temperature, and a related concept is radiation introduces a sort of embrittlement. So, what they do is they keep test specimens in the reactor and take out periodically and test its ductility. It is done, that is why you have robots are used, and you have because it is all nuclear, you have exposure to radiation. In fact, robotic technology got developed purely when they have to handle things related to nuclear installation to start with. So, they have to take out the material periodically, test specimens are kept inside the reactor, take out periodically and conduct the complete test without any human intervention. It has to be done by robotic arms and tools and so on and so forth, and this is how you have to monitor any of those installations. So, what you find from a Liberty ship failure is a ductile material can become brittle. So, that is the important learning that you gain from that, and it all started from the failure of this ship, and this was docked in the yard. This is what is important. It is not that this failure has happened in heavy sea. Heavy sea, people would have ascribed this to very heavy loads that is coming up because of high waves and or some bomb has been dropped onto the ship, some such explanation you can give, but you do not expect a ship kept in the yard to break. So, that alerted it is something to do with the structural design and the environment. And if you really look at during the first half of the 20th century, for typically high grade ship steel, the ductile to brittle failure transition was only 10 degrees centigrade. That is too high, because the operating temperature is far below this. You never had this kind of an exposure earlier. If they had stuck only with riveted ships, cracks would have formed, but they would have got stopped in another rivet hole. In a welded ship, what happened was there was nothing to arrest. So, the crack has gone through the full ship and fracture occurred. They would not have got alerted. Transition in temperature is a major cause, and there is also data associated with these failures. And as I have mentioned it earlier, below the NDT you find the ship broke like glass. That means without warning, suddenly the ship breaks into two. It is very dangerous. There is not even time for you to escape out, and in fact such failures have happened, and it has been recorded and analyzed. What you will have to look at is people have analyzed all those failures, and several such graphs are available, and what you find is the ship is designed within the first few years you had so many failures. This is something unhealthy, and this gives for a period from 42 to 52, and you also have another set of graph which shows the condition at sea. I think you need to make a copy of this, because the focus here is there were failures in heavy seas about 154, in moderate sea condition it is about 20, when the sea is calm it is about 23. That is what alerted the scientists to look at critically what has caused the failure. And if you find this, in this kind of situation, the temperature is 8 degrees centigrade below the heavy sea temperature. So, this all came about by looking at critically what has caused the failure. So, from that data you are able to segregate and find out even under calm sea conditions failure could happen, and it has happened. And finally, you do not have to feel that the design was very bad, you still have a nice Liberty ship available. Out of the many ships fabricated, 2 still remain, and it appears now you can go for a jolly ride in this. They remember this nostalgic memories, and what is recorded is out of the 2751 ships built between 1941 and 45, only 2 remain afloat, and it is all named on the soldiers who fought in this war, SS John W. Brown, and another one is Jeremiah. And right now you have special cruise aboard these ships are arranged even now. And if you really look at the modern development, you had seen the ship steels in the middle of 20th century had this NDT as something like 10 degrees centigrade. Now it has been brought down to something like minus 4.5 degrees centigrade. This is one aspect of it. That means when there is a failure, improve the material. So, people have studied the material and they have been able to bring down this nil ductility transition temperature. So, the new steels are like that. Another improvement is you bring in inbuilt crack arresters as part of your design. And what do these crack arresters do? They prevent easy crack propagation. So, that is the way you have to handle fracture. You have to find out some way to improve your design and also salvage. When there is a crack, you do not allow it to propagate easily. So, in this class what we have looked at was we started looking at the fatigue test, and the focus was you only find out the number of cycles for the specimen to fail. You do not take any note of how the crack propagates while you perform the test. Then we looked at what are all spectacular failures. Of the 4, we have been able to see 2 of them. One is the Boston molasses failure, another is the Liberty ship failure. And what I pointed out was people were not detracted by the failures, they took this as a challenge, and the failures were systematically analyzed to cull out relevant data to improve future design. Thank you.